Let's talk about error correction and its relation to Hamming distance in channel codes. This video is more or less a continuation of a previous video on error detection Hamming distance, so please watch that video before coming back here. Let's lay down the context again. So we start with a message word, which is a vector of information bits. We apply channel coding to M and we get C, which is a code word. These are the bits we will transmit. After transmitting through a communication channel, which you are modeling as a binary symmetric channel, we receive a vector called C hat. Now C hat may either be the same as C or some of the bits may be flipped. The goal of channel decoding is to convert C hat into an M hat, which is an estimate of what was transmitted in the information bits. Hopefully, if we do our channel coding correctly, then M hat will be equal to M. In the video on error correction, we were asking the question, is C equal to C hat or is C hat equal to C? If we can tell C hat is not equal to C, that is called error detection. In error correction, we are basically going from C hat to M hat, and that is the channel decoding process. So what does it mean to do error correction or channel decoding? So we have our received vector C hat at the output of the channel. Then the biggest step in channel decoding is going from C hat to C tilde, which is our estimate of C. So we have a received vector and we want to figure out what C was, right? So this is different from error detection, where we are just asking the question, is C hat equal to C? In error correction, we are saying if you received a C hat, what was the exact C which was transmitted? Now, once you know exactly what was transmitted, then you can just do the inverse of the coding process to get your estimate of what the message was. So now then let's look into the principle behind going from C hat to C tilde. The receiver uses maximum likelihood detection to go from C hat to C tilde. Before stating the principle of maximum likelihood detection, let's first note that the receiver knows the set of all code words which the transmitter is transmitting. That means, so even though at any given instant it does not know which specific C was transmitted, it does know the big set of all the possible code words the receiver can transmit. Okay, so given that, so let's state the maximum likelihood detection. So the receiver is asking the question, given that I received a C hat, which of the valid code words is most likely to have been transmitted? If we want to state this using the probability notation, so this is the mathematical expression. So the C tilde given a C hat will be the argument of maximum over all code words Ci. So for each Ci, we will calculate the probability that we received the specific C hat we received given that Ci was transmitted. And then we're going to pick the Ci with a maximum such probability. Let's look at an example to see how this works. Let's say these four are all the possible code words which the transmitter can transmit. So this is the set of valid code words. And the transmitter received a C hat which looks like this. Note that C hat is not a valid code word. So the receiver immediately knows that there is an error. But here we're talking about error correction. That means we have to pick one of these code words which we think was transmitted. Let's label the code words C0 through C3. So there are four different valid code words. And we can see that if C0 was transmitted, there had to be 4 bit flips in order for us to receive C hat. We can then calculate the probability that we will receive a C hat given C0 was transmitted. So this will be, now that the first bit, there is no error, so the probability of that happening is 1 minus p. The second bit, there is an error, the probability is p. Third bit, there is a probability p, and so on until 4. So we have p to the power 4. So where p is the probability of bit flipping in the binary symmetric channel. And we are assuming that a second bit flipping is statistically independent to the first bit flipping. Similarly, if C1 was transmitted, then there would have been only one error for us to receive C hat. If we calculate the probability that we received C hat given C1 was transmitted, it will be, okay, so the first two bits are not error, so that the probability of that happening is 1 minus p squared. The third bit is in errors, we have a probability p, and the last two bits are not in error, so that will be 1 minus p squared. So the probability of C hat given C1 will be p times 1 minus p to the power 4. So now we can ask which of these two probabilities is bigger, if probability of C hat given C1 or probability of C hat given C0. I mean, intuitively we can already say that, it is more likely to have that there is one error than there are four errors. But we can do more systematically and see if that is indeed true. If we take the ratio of these two probabilities, which we call the likelihood ratios, likelihood ratio because each of these is called a likelihood, and therefore we're calculating the likelihood ratio. This will turn out to be 1 minus p divided by p whole cubed. If the probability p of bit flipping is less than 0.5, then 1 minus p will be greater than p, and this ratio will be greater than 1. Therefore, if p is less than 0.5, then probability that C hat given C1 is greater than probability of C hat given C0. And it makes sense that probability is less than 0.5 because, we have a binary symmetric channel, and if it cannot be that the probability of it flipping bits, it cannot be that the likelihood that it will flip bits will be higher than the likelihood that it will not flip bits. If that is the case, you can just reverse the output at the channel and then you'll have p less than 0.5. Okay, so we'll always assume p is less than 0.5, in which case in this example, probability of C hat given C1 is greater than probability of C hat given C0. So instead of repeating this ratio calculations for every possible pair, let's see if we can generalize this calculation. Let's say small d is the Hamming distance between C hat and Ci. Then the probability that we received a C hat given Ci was transmitted would be, note that there have to be d flips and n minus d no flips. So the probability of that happening is be p to the power d times 1 minus p whole power n minus d. Here n is the length of the C hat vector, or it's also equal to the length of Ci's vectors. Let's slightly modify the notation and say this is di, and therefore this will be di and di. Let's take another vector Cj, or another valid code word Cj, and the Hamming distance between C hat and Cj is dj. Using similar arguments again, the probability of receiving C hat given Cj will be this. Then if we calculate the likelihood ratio again, we get this expression here, 1 minus p divided by p to the power dj minus di. Again, if p is less than 0.5, which we can always assume, this means 1 minus p divided by p will be greater than 1, which implies that the probability of receiving C hat given Ci will be greater than the probability of C hat given Cj if the Hamming distance between C hat and Ci is less than the Hamming distance between Ci and Cj. So which means if we come back to this example here, then if you receive a C hat, in order to select which of the specific code words was transmitted, or which of the code words was most likely to have been transmitted, all we need to do is compute the Hamming distance between C hat and all the code words. So in this example, it turns out for C2, Hamming distance between C hat and C2 is 4 and C hat and C3 is 2. So the code word with the minimum Hamming distance to C hat is C1. Therefore, the receiver will say it is likely that C1 was transmitted. Note, however, that the receiver could be wrong. Just because C1 is the most likely candidate, it does not necessarily mean C1 was transmitted. So for example, C3 could have been transmitted and there were two errors and we received C hat. Yet the receiver will have to choose C1 based on maximum likelihood criteria. So when can we guarantee that the receiver will be correct. In this example, we can say that if we restrict the number of errors to at max one error, then we can say that the receiver will be correct. Because let's say C1, we receive C hat, right? And if we know the number of errors is limited to one, then the only possible way we can get C hat would be if C1 was transmitted, right? Everything else need more than one errors to get C hat. So can we make any statements like that in general? Let's consider a situation where you have two code words CI and CJ, and the Hamming distance between CI and CJ is 3. This means you need 3 bit flips to go from CI to CJ, represented here, 1, 2, and 3. And then the first bit flip gives you CP, second bit flip gives you CQ, and the third will give you CJ. If the receiver receives CP, that means C hat is equal to CP, note that the receiver will make a decision about what C tilde based on the closest valid code word to CP in terms of Hamming distance. So in this case, Hamming distance between CI and CP is 1. Hamming distance between CJ and CP is 2. Therefore, the receiver will say it's likely that CI was transmitted, and therefore C tilde equal to CI. Let's say CI was transmitted and there was one error and you received a CP, and the receiver says, okay, C tilde is equal to CI, then the receiver will be correct. But if CI was transmitted and there were 2 errors and we received a CQ, in this case, the receiver will say CJ was transmitted and the receiver will be wrong. Let's take a more general case where the Hamming distance between CI and CJ is equal to D. That means in any path from CI to CJ, you have D edges. If the D edges, that means there are D minus 1 nodes in the path other than CI and CJ. Of those D minus 1 nodes, D minus 1 over 2 will be closest to CI, and D minus 1 over 2 will be closest to CJ. Let's say CI was transmitted, and there were some bit flips, and we received one of these D minus 1 over 2 code vectors. Since these are closest to CI, the receiver will still say CI was transmitted. That means any errors up to D minus 1 over 2 will be corrected by the receiver. Which brings us to this theorem. A code with a minimum Hamming distance capital D can correct any error pattern of D minus 1 over 2 or fewer errors. And the symbol here means the floor function. Right? If D is odd, then D minus 1 over 2 will be an integer. If D is even, then you need that floor function over there. Okay. Moreover, there is at least one error pattern, D minus 1 over 2 plus 1 errors, that cannot be corrected reliably. So if there are more than D minus 1 over 2 errors, then there is, let's say if CI was transmitted, then C hat will be on this side, on the side of CJ, and therefore the receiver will say CJ was transmitted and you'll make an error. Okay, so that's what this theorem says.